So good morning, everyone. Today I'll be solving the Leetcode hard question called word ladder. So, like it will be to a similar theme to my earlier questions, mainly centered around BFS, DFS questions. So this question is mainly a little bit different. Like unlike the others, it's not implicitly a BFS or a DFS question, but it can be looked as one of them. So I'll tell you after I finish this question an easy way to identify when to use BFS in this way. It's an implicit graph. Okay, so here's the question. On the face value, it's very simple. You're given a begin word and an end word, so hit and cog, and you need to see how many transformations should you make to hit to become a cog. So right now you have hit. Now when you make when you make the I into an O, you get hot. After you make the H into a D, you get dot. Then you make the T into a G, you get dog. Then you get lot, log, cog. So that's the thing. So that's the transformation as it's shown here. So the thing is, you are only allowed to move into these transformations that they have mentioned here. So any other transformation you're not allowed. So for example, from hit, you can only go to hot. That's the only way because there's no other combination with HOT. There's no hog or something else. You can also, yeah, in this case, I think that's the only one. Once you get hot, you can go to both dot and lot. So they're given two options to explore from then onwards. Similarly, so now here from hit to cog, when this is the word list, so you have five transformations to reach here. And in this case, from hit to cog, there's hot, dot, dog, lot, and log. As you can see, from hit, there is absolutely no way you can actually end up here because unlike these two, you don't have the end word cog even here. So you'll never reach that point. So I'll tell you how we can approach this using BFS. Alright. So like any BFS questions, for first we'll import the queue deck. So a deck is what the Python inbuilt function for a queue is. Alright, so let's start. So first things first, we need the word list properly. So let's have the word list, right? So we can store, we are given the word list so we can make it into a set so it's easier to search for it. Alright, so we can have a word list and we can call it set of word list. Alright, so we have this set ready. Now we also need another set for visited. So what this visited set is, once you already reach one of these combinations like hot or any of them, you don't want to go back and then iterate from there further. Alright, so now to begin with, let's also add, okay, so let's add the first. Okay, so this is how the BFS approaches. So like any BFS approach, we first start with the initial value in the queue. So we append the initial value into the queue. So that would be queue. Let's first initialize the queue and then append it. So what is the initial value? The initial value is nothing but begin word, right? And what is the length of the begin word? So we initially start with 1 because from whatever word you start with, like it's mentioned here, the begin word does not need to be in the word list. So we start from the begin list and then we count the transformations. So because obviously from hit to hot you need 1 transformation, from hot to dot you need 2, dot to dog you need 3, dog to lot you need 4, like in this case, yeah. Lot, okay, so in this case, yeah. From hit to hot, you need 1, that's the first one. Then to dot 2, then to dog 3, then to cog, which is 4. In that, in total, it becomes 5 because it's 4 transformations but 5 words in total. That's why we begin with 1. Otherwise, we would have begun with 0. Alright, so now let's start. So now, while there is an element in the queue, let's first have the size of the queue is equal to length of the queue. This is a standard approach to BFS. If you follow my earlier questions as well, I do this in almost every question so that you just have an access to the outer layer. Alright, so for I in range, you can directly start with the popping elements, but I like doing it this way. So now while you iterate to the queue, alright, so let's get the first element. So what is the thing? We get the word. So let's get the word and the number of transformations, because that is what we have here. 1, alright, is equal to q dot pop left. So we pop the first element in the queue. So in this case it would be hit, because that's the only element you're adding to the queue in the starting. All right. So now we need to go through all the possible mutations from queue. So how would we approach that? So here we also have to implement the logic of if we find the transformations, if that is required. So let's do that. If the word is equal to the end word, in that case we will return the number of transformations, because yeah, so in this case if the word is just directly you get whatever you require, then it's just one transformation, so we don't really need to do any transformations and you can return it. All right, so now let's begin. So now for the other word, right, so we need to go through all the words, possible words, let's just call it possible word in. Okay, so now we need some way that we can get all possible valid mutations from hit. So in this case, the valid mutations from hit is just hot, because there's no other. You can have like, this is hit, right? So if you consider it, it would probably be around 3p3 combinations. So you have three words. Sorry, not 3p3. It's 26p3, because you have 26. It's permutation. So you have 26 letters. Each letter can have one of these 26 letters. Minus 3, because obviously you won't have it as hit, you won't have HIT on its own. So if you consider it that way, minus 1, sorry. So if you consider it that way, and but the thing is, out of all those numbers, out of all the 26p3 numbers, the only ones you have to consider are the ones that are in the word list. All right, so we will have a separate functions generate words of that word that you are generating here. All right, so this will return, this function generate words, which we haven't defined yet, we will define soon. So this a function to generate valid words. All right, so define generate words, and you take a word array and pass. All right, let's just leave it blank for now. Pass is just to make sure it's valid. We'll just keep it like that for now, and we'll implement that later on. So now once we get a possible word, what do you want to do with that possible word? So one thing is for sure is we need to add it to the scene array, right? Possible word. All right, so we have added it to the scene array. Once you have added it to the scene array, what you have to do, you have to append it to the queue. So you have to add the possible word, and you also have to add the number of transformations. Now, since you have done a transformation here in the generated word, you have to do number of transformations plus 1, if you think about it, right? Yep, so you have to do it plus 1. So now we add that to the queue as well. Now, once it's done, if for example you do not have any valid words so that the queue is gone, then you have to return 0, since you have to return 0 if there is no such sequence. All right, the queue is here. Yep, so return 0. This will be a standard case. So this should work. Now let's just define this function. All right, I'll give you an easy way to do this. All right, so now first things first, we need a words array, which will have the list of possible words that we can generate from here. So the easiest way to do it, since you don't you have to make it a 3-letter word only. For I in range, how much is that? Length of the word that you're giving. So in the starting case, you're passing hit. So when you pass hit, length of word will be 3. So we have to do for all possible 3s. Now for, this is very important, character in, what are the words? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Alright, so these are the possible characters you have. Alright, so now this is very important. New word. Let's have the new word. What will be the new word? Suppose you want to change just one element in this. So in the starting, so in this case, right, as you can see, it's I in range. So what do we need? So for every this, let me show it to you here. So what we need to do is we need to get this word. So in this case it's A, and then we need to, up to I, we need to keep the string as it is. String cannot be mutated. We cannot just change word of I like this. Word of I, we cannot just make it like what word of I. is equal to character, because string is immutable, remember that. So the best way to do it is to add whatever is there before the string as it is, and then whatever is there after the string. So let's say, for example, the word is hot. So the best way to do it is you need to add all the elements up to I, and then you add the word, you add the character, the new character, whatever you require, and then you add everything from I plus 1 onwards. So this way, what you get is, suppose the I is 0. So now we're changing the first letter, and then the character is A. Alright. So how will hot transform in that case? It would become AOT, because up to I you're keeping the same. So up to 0 you're keeping the same. In this case, it will be HOT up to 0 is the same, means it will just be here. It won't change anything on the left. Then you append the character. So you have A added, and then from I plus 1. So in this way, string is inclusive. So from I plus 1 onwards, it will be the same. So OT will remain as it is. So this will get transformed to hot will become AOT. Similarly, if I is equal to 1 and the character is A, up to 1 it will remain the same. So H will remain the same. Then it will add the character A, and then after I plus 1, in this case it's 1 plus 1, 2. 2 onwards it will remain the same. So T, it will be the same. So that's the way we will do the transformation. So yeah, let's do it here. So the new word will be nothing but the current word, whatever we have, up to I plus the character that we are going through. So what that will do is it will go through all of these characters A to Z plus word of I plus 1. So this will generate the new word. So now, very important. First things first, we have to check if new word in the word list. Remember that, that's very important, right? The new word we generate should be in this list. And we have created a set called word underscore list. This, what they have is a list. We have an array. We have a set. Set is O of 1 search time. So it's if it is in the word list, and the new word should not be in the visited array, not in visited, because the visited array is this one. So if you've already visited, there's no point adding that to the possible words. If this is true, what do? We add it to the words array. Words dot append new word. Alright, so you've got the new word, and at the end of this entire thing, you have the words is populated with all the possible words that you can generate from the words array. So what you can do is words, return the words array. Return the words array. Alright, that's perfect. So what this will do is it will generate all the possible valid words that you can generate from a particular word. So now once you have that in this generate words. Now you append it to the queue, and each time once you reach the target, it will return the number of transformations. If you've already exhausted this entire list and clearly there's nothing remaining in the queue, so there are no possible words remaining, it will come out of the loop and return a 0. So let's test if this works. Okay, there's one thing I forgot to do. This is a tuple. I need to return this with an extra bracket. Yep. Yeah, here as well. Yep, you need to return a tuple because Q can have only one value. Yep, this works perfectly. 5 and 5, and let's submit it. See, perfect, it runs. So yeah, about this question, usually whenever you have something based on transformations or branching out methods, it's always preferred to use a BFS because it works really well. You don't need to apply any complicated logic of trying to generate like thousands of combinations and things like that. This works really well. So there are a lot of similar questions to this in the similar manner. So if you look at similar questions, you have minimum genetic mutations. It's another question I've already solved. It's also has a very similar problem. So if you guys really want to try this, you can try this as well. There are so many questions like this where you can just think about it. You solve one question of this method, you'll get the idea and then you can solve it. So thank you so much for watching. I will be uploading more videos for my reference. If this really helps you, it's amazing. Thank you so much.